Hi everybody, this is Dr. Kat Vlies from Central New Mexico Community College, back with CNMGlass. In the previous video, we learned that muscle fibers are stuffed with lots and lots of these specialized organelles that we call myofibrils. And remember that myofibrils are surrounded by sarcoplasmic reticulum. What I'd like to do now is show you what we find inside of the myofibrils. So if we have, and this is a little difficult to sketch, so bear with me. So if we're looking at just a portion of a myofibril, remember there are these long angel hair pasta-like organelles, we find that on the inside are all these proteins that we'll learn about next. And they're organized into what we call sarcomeres. And you're going to quickly see now how these arrangements of proteins into sarcomeres create the striations as well. So I'm going to make an attempt to draw a couple of sarcomeres here inside of my myofibril. And remember, you have lots of myofibrils, one after the other, one next to the other inside of a myofiber. So we have these zigzag or these proteins, I should say, arranged in a zigzag manner, and they form anchor points for one of our proteins, which we will refer to, or a set of proteins that we will refer to as the thin filaments. So let me finish these so-called Z lines or Z discs, because they form the beginning and the end of one sarcomere. Remember, sarc or sarco refers to muscle, and mere, think of the term polymer, or monomer means unit. So sarcomere literally means the unit of a muscle cell, more specifically the functional unit. We're going to see that it's at the level of the sarcomere that muscles contract. So I'm going to draw one more sarcomere next door to this one inside of the same myofibril, and I could possibly draw another one, but let's get started with just this. We find that attached to the Z lines are what we call our thin filaments. And they do not touch. So they arise from these Z lines as such. And as I said, they do not touch. So these are our thin filaments, and their main protein is called actin. So we can also call them actin filaments. Notice that we're dealing here with yet another F word. We've gone from a muscle organ filled with fascicles, which in turn are filled with fibers, which in their turn are filled with myofibrils. Here we're looking at one. And then we see that a myofibril is full of sarcomeres made up of filaments, not just thin filaments. And let me finish my thin filaments here, but also thick filaments. And the thick filaments sit in between, like the thin filaments, almost more or less like this. And they have these heads sticking out. Again, this is very sketchy. I'm not going to draw the heads everywhere. I'll just draw a few here and there. But there's many, 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 many of these heads. And these thick filaments are anchored as well. I'll show you this in just a moment. Let's first label these as our thick filaments, and their main protein is myosin. And so we can call them myosin filaments if we'd like. It's easy to remember that the thin filaments are called actin because tin sounds a lot like thin. That's how I keep track of things. The thick filaments are characterized by these head-like structures sticking out. And the reason for this is because it's these little head-like structures that can grab onto our thin filaments and pull the thin filaments into the space right here, as well as right here. That space we refer to as the H zone. So from here to there, we call that the H zone. The H stands for hell, which means in German, it also means, aside from hell in English, it means bright, because it shows up as a lighter band under an electron microscope. But I forgot to tell you what the thick filaments are anchored with. The thin filaments are anchored with the Z lines. The thick filaments have a similar protein, or an analogous protein, I should say, and we call it the M line. So the M line is made up of proteins that hold on to our thick filaments. The final thing we now need to point out is the fact that we have areas where we have just thin filaments and areas where we have both thick and thin filaments. The areas where we have both thick and thin filaments are actually corresponding to the length of our thick filaments. So if you take a look here, from here to there, which is the width of one thick filament, notice that you have thin filaments in this region as well. We call that the A band. And so here again, from here to there, we call that the A band. In between consecutive A bands, we have the I band. So from here to there, we call the I band. And the A and the I stand for words that relate to photography and how these particular regions of our sarcomere reflect light under a microscope. And so we find that the A band, which has both thick and thin filaments in it, both thick and thin filaments, that band looks a lot darker under the microscope, with the lighter H zone in between or within, compared to the I band. The I band only has thin filaments with the Z line, and therefore it looks a lot lighter under the microscope. So the striations are formed by the A and I band, and the A and the I band, and the A and the I band. Now what I have shown you here are two consecutive sarcomeres inside of a myofibril, inside of a muscle cell that is relaxed. So this is a relaxed muscle cell with a myofibril illustrated along with two sarcomeres, and I could go on with sarcomeres. Let me now give you a little bit of a preview of how muscles contract, and I kind of did that already, but let me repeat myself. So when a muscle cell is stimulated by when skeletal muscle cells are stimulated by the somatic nervous system to contract, the way they do that is by the heads grabbing onto these thin filaments when they can, like so, and they move the thin filaments into the H zone. So all of these thin filaments are going to be pulled into the H zone. And ultimately, that leads to this whole myofibril, as well as the other myofibrils, which are going through the same process to start to shorten. And that, of course, impacts the whole muscle cell. Now imagine that quite a few muscle cells in a muscle organ are going through this process. Clearly, that's going to cause the whole muscle organ to begin to shorten. Now I have to be careful because I cannot make you think that the moment that our heads grab onto our thin filaments, our muscles go through the process of contraction or shortening. We can't use the term shortening as a synonym for contraction. Contraction refers just to the binding of the heads to the thin filaments, and different things could happen. But most of the time, when we see that the muscles can start shortening, we tend to think of contraction as shortening. That seems a little confusing, but you'll see with time this will begin to make more sense. And so here we've learned about a sarcomere. Where did I write that down? Right here. And many, many sarcomeres, one next to the other, form a myofibril. We have many myofibrils surrounded, wrapped up in that sarcoplasmic reticulum inside of a muscle cell or muscle fiber. And we have muscle cells inside of fascicles and many fascicles inside of a muscle organ. Thanks for watching. Till next time.